Alright, so I think this is recording. Let's take a look at these problems. The first few is really out of memorization. Remember that for the inverse of a function, you switch domain and range. And a function, when you look at the inverse relation, that inverse relation may not be a function. We want the inverse relation to be a function, so we restrict the range of these inverses so that they will pass the vertical line test. So the domain and range. The range for this inverse cosine used to be the domain, and the domain used to be the range. So from negative infinity, or excuse me, -1 to +1. Now, the domain used to be all real numbers, but we need to restrict it. We need to restrict this range so that it will pass the vertical line test. And for the inverse cosine, we restrict it to be between 0 and pi. Alright, for the inverse tangent, the range used to be all real numbers, so now the domain is all real numbers. We need the inverse relation to be a function, so we restrict the range, and they've just agreed upon this definition of restricting the range to be between -pi/2 and +pi/2. And for the inverse sine, it's very similar to the inverse tangent, except we'll include, see, the tangent of -pi/2 and the tangent of pi/2, the tangent of any odd multiple of pi/2 is going to be undefined. So here, our domain, -1 to +1, which used to be the range of sine, and now the range, instead of the domain being all real numbers, we restrict it so that this range will pass the vertical line test. So there we go. Alright, now the inverse tangent, the tangent of 0 is 0. We know it's going through the origin. We just got done saying that the domain is all real numbers, and the range from -pi/2 to +pi/2, and pi/2 is approximately like 1.57. So from here to here, this is a horizontal asymptote, so is this. So this inverse tangent, because this is approximately -pi/2 and +pi/2, because, well, it'd be actually a little bit higher, 1.57, but it's got to be graph A. The inverse cosine, we know the domain's from -1 to +1, and the range is from 0 to pi. So here, and pi is about 3.14, so it's got to be B. The range that we want for inverse sine is from -pi/2 to +pi/2. So if pi/2 is 1.57, here's 1.5. That's why it's going down just a little bit below that and a little bit above that. So this is D. You'll have your unit circle on this. Let me pause this and go get a copy of that. So I'm back. The inverse sine uses just the right half of the unit circle. We restrict the range, the output of this, to be between -pi/2 and +pi/2. We look for a y-coordinate that is radical 2/2, and we find it here at pi/4. So for the inverse cosine, we use the upper half of the unit circle. We're looking for an x-coordinate that is negative radical 3/2, and we find it here at 5pi/6. For the inverse tangent, we use the right half of the unit circle. However, at pi/2 and -pi/2, it's undefined, so we're not using those endpoints. And we're not looking specifically for any points. We're looking for a ratio. We want the ratio of y to x to be 1. So therefore we want the x and y coordinate to be the same, and we see it here at pi over 4, that if you take the radical 2 over 2 divided by radical 2 over 2, that it's 1. So it's this point, and we use that angle pi over 4. Arc cosine uses the upper half of the unit circle. We're looking for an x coordinate of radical 2 over 2, and we find it right there at pi over 4. For the inverse sine, we use the right half of the unit circle. We're looking for a y coordinate of negative 1/2. Now we've got to be careful. If we say 11 pi over 6, that's not between negative pi over 2 and positive pi over 2. So we need to find a coterminal angle. So we actually subtract 2 pi. So if you go clockwise to get to that point, that angle is negative pi over 6. The inverse sine uses the right half of the unit circle. It's positive, and we're looking for a y coordinate radical 3 over 2, and we find it. Oh, boy, I'm going through. Notice that the directions changed. This isn't a capital S anymore. So I'm not just using the right half of the unit circle. I'm using the entire unit circle. Sorry about that. So I look from 0 to 2 pi for a y coordinate, it's radical 3 over 2. And I find it, yes, at that point, but also over here at this point. So I have two solutions. One at pi over 3 and one at 2 pi over 3. Because see, there's infinitely many values of x that satisfy this equation, but only two of them that are between 0 and 2 pi. Alright. So yeah, same thing. This inverse is an inverse relation. It's not a function, so I can get more than one answer. In fact, I would get infinitely many answers if I weren't restricting myself to just be between 0 and 2 pi. See, the capital inverse restricts you to be between 0 and pi, and that will only give you one answer. But between 0 and 2 pi gives us more than one answer. It gives us two answers. That's why that's not a function. So we look for an x coordinate that's negative radical 2 over 2. We find it at this point, but yet also at this point. So there's infinitely many answers for x, but the two answers that are between 0 and 2 pi are 3 pi over 4 and 5 pi over 4. So for the square root of 3, I'm really looking for a y over x that has a ratio of square root of 3, and I see it right here at pi over 3 that if you take radical 3 over 2 and divide it by 1/2, you'll get radical 3. So I get it here, and the period of tangent is pi, so I'm also going to see that same ratio. If I add pi to it over here in the third quadrant, you can see that when I take y divided by x, that the negatives just cancel, and I get a ratio of radical 3. So of the infinitely many solutions that there are, only two of them are on 0 to 2 pi, and that's pi over 3 and 4 pi over 3. Now, of these infinitely many solutions that satisfy this equation, they only want us to list the ones that are between negative 2 pi and positive 4 pi. We could get the general solution and then just substitute in values of n. That's typically how I would always suggest doing it, unless you just visualize going clockwise one rotation and then counterclockwise two rotations. Going clockwise one rotation, you'll pick up two solutions, and then going counterclockwise to 4 pi, you'll pick up 4 more solutions. There'll be 6 answers for this problem. Let's go ahead and write the general solution and then show those 6 answers. So if I look on the unit circle for an x-coordinate of negative radical 3 over 2, I find it at this point, and I find it at this point. So I can write this 5 pi over 6, and the period of this is 2 pi, but I'm going to write 2 pi as 12 pi over 6. So now, by substituting in different values of n, I can provide you answers that are between negative 2 pi and positive 4 pi. Since this has a denominator of 6, let's rewrite this negative 2 pi as negative 12 pi over 6, so we can easily see when to stop when we don't want to be below negative 12 pi over 6. And over here for 4, 24 divided by 6 is 4. So if I let n be negative 2, negative 24 plus 5, negative 19, that's too small. If I let it be negative 1, I have negative 12 plus 5, negative 7. So negative 7 pi over 6 satisfies this equation and is also between these two values. If I let n equal 0, 5 pi over 6, 5 is between negative 12 and 24, and it satisfies that equation. If I let n equal 1, I'll have 17 pi over 6, that satisfies it. If I let n equal 2, 24, plus 5, then I'll be bigger than 24. So for this point x1, these are the 3 solutions it provides. Now remember, I said there were 6 solutions. We can get 3 solutions that are between negative 2 pi and positive 4 pi if we come down here and look at this second point at 7 pi over 6. Again, since the period of cosine is 2 pi, I'm going to add that period, but I'm going to write 2 pi as 12 pi over 6. And if n is negative 1, then I've got negative 5 pi over 6. Negative 5 is between negative 12 and positive 24. If I let n equal 0, I've got 7 pi over 6. If I let n equal 1, I've got 12 pi over 6. So here's the 6 solutions that satisfy this equation that are between these two values of negative 2 pi and positive 4 pi. Without that restriction, there would have been infinitely many solutions that satisfy this equation, given by this general solution that I have for x1 and this general solution that I have for x2. Here, rather than radians or want me to work in degrees, I'm looking for a ratio of y to x that's negative 1. I'm going to find that in quadrant negative ratios for tangent in quadrants 2 and 4. If I divide the y divided by x here, I'll get negative 1. And if I divide y divided by x here, I'll get negative 1. So one of the solutions, 135 plus any coterminal angle to that. Well, actually the period is shorter than 2 pi. It's pi. So I can describe all infinitely many solutions, not pi. I'm working in degrees, so 180. Like this. Alright, so if we let n equal negative 1, hmm. 135 minus 180. I'm getting negative 45 degrees. But what if I took 135 minus 360? Oh yeah, okay, there I had one. Because I'm still bigger than negative 360. So I got negative 225, negative 45. Let n equal 0, and I've got 135. Let n equal 1, and I've got 135 plus 180. 315, and if we add any more to that, another 180 will be above 360. So of the infinitely many solutions that satisfy this equation, there's 4 that are between negative 360 degrees and positive 360 degrees, and we found them right here. Now there's infinitely many solutions to this equation, and they want me to write an expression that represents that infinite list. So let's use our unit circle. We know that from 0 to 2 pi there's 2 points that have a y-coordinate of positive 1/2, here at pi over 6 and at 5 pi over 6. So if I take pi over 6 and add 2 pi in, I'm going to write 2 pi as 12 pi over 6. So that describes infinitely many solutions that satisfy this equation, and they're all in relationship, related to this point and its coterminal angles. And let's go over here to this other point, 5 pi over 6 plus 12 pi over 6 n. So those are our 2 equations that describe the infinitely many solutions. It said all possible for this equation. Alright, now since this is a capital C, this is a function, and every input will have exactly one output. I'm not going to see this 4 to 5 as an x-coordinate on this unit circle, so I can just sketch my own unit circle, and I know that on the upper half of this there is at least one point here in quadrant 1 that will have an x-coordinate of 4/5. So I'm going to have to use my calculator to have it tell me what this angle is. So it wants us to be in radians. So check your mode. Right now I'm in radians, and it wants to the nearest thousandth, to the nearest 3 decimals. And if I take inverse cosine of 4/5, 0.644 is what I'm getting. This angle measure in radians is 0.644 radians. Now, I'm a lowercase letter. There's infinitely many solutions to this equation. They want me to look at the ones that are between 0 to 2 pi. There's a typo. I can't give an exact answer because I will not find this ratio on my unit circle. It is between -1 and +1, so I know that a point exists with a y-coordinate of -6/11. It's just that you won't find it on this circle. You won't find a y-coordinate at these designated points. So I know that down here in these 2 quadrants are 2 points that are -6/11 below the x-axis. Alright, if I use my calculator, it's going to tell me, it's going to use this point, and it's going to give me a negative angle measure to get there. But see, it wants me to have it bigger than 0. So let's use the calculator to get a solution to this equation. Second inverse, let's look and see, are we in radians? Yep. And I'm at 3 decimals, and that should be fine. Let's go -6 divided by 11. And this angle measure of -0.577. So yes, it's a solution to this equation. If you want to call it x, you can. It's a solution to this equation, but it's not bigger than 0. So maybe I shouldn't call it x. Maybe I should call it theta to indicate it's a solution of the equation, but it doesn't fall into the restriction of it being between 0 and 2 pi. So if I find a coterminal angle to this, If I go back to my calculator and just add 2 pi, uh, 5.706. Now, that's this angle, which I've skipped over that point. So I need to come back and pick that point up. I know that there's an angle in the third quadrant that also has a y-coordinate of -6/11. So I need to use this reference angle right here, which is the same as the reference angle there. And remember, reference angles are positive. They're between 0 and pi/2. So my reference angle is just positive 0.577. So this angle that I want for my second solution is pi plus this reference angle of 0.577. So if I come back, the inverse sine of 6 divided by 11 will give me that reference angle, and then I want to add pi to that. So 3.719. So of the infinitely many solutions that satisfy this equation, the two that are between 0 and 2 pi are 5.706 radians and 3.719 radians. So the inverse cosine, if I go to a calculator, it's going to treat it like a function, and it's only going to look in the upper half. But that's a lowercase letter. I know that there's an x-coordinate in the first quadrant that has 0.774, and there's a point over here in the fourth quadrant that also has that. So if I go to a calculator, it's going to give me this angle. So let's call that x1. Let's come in, punch that into a calculator. I'm still in radians. I'm still rounding to the third decimal. The inverse cosine of this 0.774 is 0.686 radians, and that's an angle measure, and that's right there. Well, that's the acute angle. To go down, to rotate clockwise, it's that same magnitude, only now it's negative. So negative 0.686. Those are the two solutions of the infinitely many solutions to this equation. There's only two that are between 0 and 2 pi. For inverse tangent, if it were a function, we would just focus our attention on the right half of the unit circle. But it's not. It's a relation. There's going to be a point in the first quadrant of y divided by x that ratio is 1.472, and then over here in quadrant 3, that same ratio, and with the numerator and denominator being negative, is going to exist. So when I use my calculator, it's going to give me this angle. So let's go get it. We're in radians and we're rounding to 3 decimals, and why is there the inverse tangent of 1.472, 0.97 radians, 0.974 radians. So that's this angle. Now for tangent, I can come over and get this angle to be on 0 to 2 pi by just adding pi to that, and we'll have of the infinitely many solutions to this equation, there's only two of them that are between 0 and 2 pi, and if we add pi to this, 4.116 radians is the second answer, and those are our only two answers. And remember that we couldn't give exact values because those weren't points on the unit circle. We're having to approximate it on our calculator, and I'm just approximating it to 3 decimals. Alright, directions have changed. It's still a relation of the infinitely many solutions that satisfy this equation. They want me to just look for the ones that are between negative 2 pi and positive 2 pi. And I'm going to have to approximate when I use my calculator. That unit circle doesn't have an x coordinate of negative 0.7 on it. So I know that there's an x coordinate in the second quadrant of negative 0.7 and also in the third quadrant of negative 0.7. If I use my calculator to approximate this angle, it's going to find the one that's here in quadrant 2. So let's go inverse cosine negative 2.346 radians. Now, my reference angle, when you're an angle in quadrant 2, it's pi minus that angle is the reference angle. So if I take pi minus my previous answer, I have a reference angle of 0.795. So if I want to get to this point and find this angle, I have to take pi, which will get me there, plus that reference angle. So my second solution is this reference angle plus pi, right? So 3.937. Now, oh, it also wants me, those two solutions are 0 to 2 pi. I just noticed it wants the negative solutions as well. So let's find coterminal angles by subtracting 2 pi from each of these answers. So there's two more answers that I can get. Sorry about that. It's Friday afternoon. I'm getting a little bit tired. So if we subtract 2 pi from that answer, so let's go back and, or if we subtract 2 pi from this, I have this answer pulled up, so let's just subtract 2 pi. So negative 2.346, and my previous answer of this 2 was inverse cosine of negative 0.7, and if I subtract 2 pi from that, that angle will be coterminal. So I claim that if you pick any one of these four angles and take the cosine of it, you'll get something very close to negative 0.7, and all of these angle measures are between negative 2 pi and positive 2 pi, where negative 2 pi is 6.281, 6.283. All of these negative values are bigger than that, and 2 pi, these positive values are smaller than it. Alright, so let's take the cosine of negative 3.937 just to check this. And I claim that we should get a value that's negative 0.7 or there close to it, and we do. Or if we took this cosine of 3.937, it may not be exact, but it'll be real close to it. There we go. All right, and you could do the other two as well, and it'll check. I'm going to stop here and do the rest later. So, hey, I'll talk to you later. Hope that helps. Bye.